Welcome to The Explainer. Today, we're going to completely reframe a concept that sits right at the very edge of human understanding. Usually, we treat the word chaos as a synonym for pure, unadulterated disorder, right? But we're going to dig into the actual foundations of chaos theory today, and honestly, it's going to permanently change how you view the universe.
Okay, let's dive into this premise. Does chaos actually come from randomness? For the longest time, the scientific community just assumed that if something behaved unpredictably, the underlying forces driving it had to be completely random. I mean, it makes sense intuitively. If the outcome is a total mess, the input must have been a mess too, right?
Well, here is the twist that absolutely upended our understanding of physics. The central discovery of chaos theory is that systems can behave completely unpredictably even when they follow strictly precise rules. So chaos doesn't necessarily arise from randomness at all. Remarkably, chaos can actually arise from order itself. To understand how scientists made this profound realization, we kind of have to travel back in time just a little bit. Section 1. The illusion of the clock. See, for centuries, humanity clung to this really comforting scientific viewpoint: the giant clock universe. Basically, many brilliant minds believed the universe operated just like a finely tuned mechanical timepiece. And the logic was rock solid. If you knew the exact position and motion of every single object, and you understood the laws governing them, then in principle, the future could be predicted indefinitely. But 20th century discoveries entirely dismantled this clockwork illusion. They revealed that perfectly understood rules absolutely do not equal perfect prediction. Some systems follow exact physical laws, yet predicting what they're going to do in the long term is virtually impossible.
And honestly, it makes sense why this clockwork view was so popular. It was enormously successful for hundreds of years. Using classical mathematics, scientists could predict the exact motions of planets across the night sky. They could map the precise trajectories of cannonballs flying through the air and flawlessly describe the behavior of complex machines. It really felt like we had cracked the code of the universe.
Section 2. The weather anomaly. But then we hit a massive roadblock in our predicting power with something we literally experience every single day: the weather. We all know the feeling of planning a weekend based on a Tuesday forecast only to get completely rained out on Saturday. Forecasts are reasonably accurate for a few days, maybe somewhat reliable for a week if you're really lucky, and much less reliable beyond that. Now, why is that? It's definitely not because meteorologists don't understand the laws of physics. The atmosphere obeys the exact same physical laws every single day. The issue is that the atmosphere is an enormously complex system where countless variables are constantly interacting.
So the crucial point is something called sensitivity to initial conditions. This is the defining characteristic of a chaotic system. Imagine measuring the temperature, the air pressure, the humidity, or the wind speed. If you have even a microscopic error in that initial measurement, that error doesn't just sit there. It interacts, it compounds, and it grows over time until it creates a spectacular difference in your forecast. Two situations that begin almost perfectly identically eventually produce dramatically different outcomes. Which brings us to a phrase you've almost certainly heard before, beautifully summarized by meteorologist Edward Lorenz: the butterfly effect. The famous image is of a butterfly flapping its delicate wings in one part of the world, and that tiny change in air pressure influencing weather patterns elsewhere weeks later. Now, to be clear, the butterfly isn't literally causing a massive hurricane. What this vividly illustrates is how tiny, otherwise insignificant disturbances are aggressively amplified by a chaotic system over time.
Let's step away from the math for a second and just picture this physically. Imagine you're standing at the very, very top of a towering, incredibly steep hill. You take a ball and you perfectly balance it on the exact peak. If you start that ball even a microscopic fraction of a millimeter to the left, it gathers speed and rolls all the way down the left side of the mountain. But start it just a fraction of a millimeter to the right, and it plunges down the right side. The initial difference in starting position is entirely imperceptible to the human eye, yet the final outcomes are miles apart. This is exactly how chaotic systems behave. Small differences become enormously important.
Section 3. Complexity from simplicity. We're kind of wired to assume that wildly complicated behavior requires incredibly complicated causes. But mathematicians discovered something called the logistic map. It's basically the blueprint of chaos, an equation so simple it only uses basic arithmetic operations. It was originally designed to model population growth in biology, but it hides a massive secret dictated by just a single parameter. Watch how this system escalates. When certain low values are chosen for that parameter, the system is totally chill.
It settles into a stable state and the population remains steady. But increase that parameter just a little bit and suddenly the stability breaks. The population starts bouncing wildly back and forth between two values. Increase it a bit more and it alternates among 4 values, then 8, then 16, until finally the pattern explodes into something so complex it appears completely and utterly random. Yet the profound realization here is that every single chaotic step of the way, it is being generated by the exact same, unbelievably simple equation. This led to a truly profound realization. Nature does not always need complicated rules to create complicated behavior. Extremely simple rules repeated over and over and over again are entirely enough to build an unpredictable universe. And the scope of this is massive. Chaos isn't just about the weather or abstract math. Chaotic behavior appears everywhere. It's in the turbulence of fluids rushing through a pipe. It's in the delicate balance of ecosystems. We see it in electrical circuits, massive chemical reactions, the beating rhythms of the human heart, and yes, even in some aspects of planetary motion that we once thought were totally clockwork. Researchers are finding that huge parts of the natural world actually operate right near the boundary line between rigid order and total chaos. Section 4. The hidden underlying order. Now, what's really interesting is that we aren't just staring into an abyss of pure randomness. Chaotic systems actually have structure. When mathematicians take this seemingly random, chaotic behavior and plot it out visually, these beautiful, intricate geometric forms suddenly emerge. These are called strange attractors, and they prove that chaos has an underlying order. The system might literally never ever repeat the exact same movement twice, but its behavior is permanently constrained within these beautiful, specific boundaries. This leads to one of the absolute deepest lessons of chaos theory. We have to separate two words we usually treat as the exact same thing: deterministic and predictable. A system can be entirely deterministic, meaning its future is completely determined by its current state and the strict laws governing it. But it can still be completely unpredictable to us. The laws are perfectly known, but because we can never measure the starting conditions with infinite, perfect precision, those tiny uncertainties will always eventually overwhelm our ability to forecast the future. So, what does this all mean for us? Well, it fundamentally changes how we view nature itself. Chaos theory delivers an incredibly humbling message. Limits to our prediction aren't just because we're ignorant or don't know the math yet. Those limits arise from the intrinsic, baked-in behavior of the universe. Simple causes generate extraordinary complexity, and order and disorder are forever intertwined. Even when the rules of the game are completely understood, the future remains wildly uncertain. Which leaves us with this final, fascinating question to ponder. If perfectly orderly rules can create totally unpredictable futures in mathematics, in weather, and in biology, how much of the extraordinary, messy complexity in our own daily lives is simply the result of tiny, immeasurable starting conditions? Think about that for a second. Think about it the next time a tiny change in your morning routine leads to a completely unpredictable day. Thanks for joining me on this explainer, and keep looking for the order hidden in the disorder.